September was Purple Month at our channel sponsor PCBWay, and I took full advantage of that. So shall we see what I got? Now you might remember that last year I made this test device for a 6532, which is a Riot chip, RAM IO timer, and this is a cartridge for a Commodore 64. This is the prototype that we built on the channel, and that was great guns. I further refined that, and I also produced a version for the 6526 CIA, and this is the latest iteration, which is a 65221, and of course this comes in nice purple. £5 for 10 boards, naturally. You'll notice on this one that I've got these little modules, whereas here I had discrete LEDs, and these are a little thing that I built on the channel to my own design, and I called it the blinking bus because it's 8 bits and 8 LEDs. So last year I designed this. This is the first iteration of it. It's got these network resistors on it. You'll remember if you watched the SMD test kit video last time that I had a certain amount of trouble with these resistor networks, and I had trouble with these resistor networks on this as well, and these are bigger ones than the ones that we did last time, and these work great in this kind of device. So I'm thinking that one day I'll sit down and make myself a sort of Ben Eater style 6502 board computer, and these are going to be great for doing bus diagnostics and things, and just general blinking lights, hence the name blinking bus. But I also remembered that on little keypad computers like the Kim 1, the Cambridge Mark 14 and so on, that they all have little 7-segment hex displays, and it would be really nice to have if you've got a bus going on here, or like on this situation you've got two 8-bit ports. So I thought it would be really nice if I had 7-segment displays that were hexadecimal, 0 to F, and that would be a really nice fun thing to have. So I sat down with KiCad and I set about trying to design one. And the interesting thing there is that you find BCD to 7-segment display driver chips are like grains of sand. So they will do decimal numbers and display them on your 7-segment display. I've got some 7-segment displays here. So here we are, standard sort of 7-segment display, common cathode, in a kind of dip package, so they go in there. You still see them all the time in clocks, and you can get display drivers for these that will take a decimal value, a BCD, binary coded decimal, and turn that into a number. And that's great. And you used to be able to get a hexadecimal one that did 0 through 9 and A through F, but they don't make those anymore. Fairly typical. This board uses them. You can get them, you can find them on eBay, you can find them on AliExpress. They're getting kind of expensive and they're getting kind of rare. But I designed that to use those chips, and I have actually got some of those. They are MC14495P, and I managed to get 10 of them, so I can build, in theory, 5 boards, or I can build a board or 2 and have some spares. That's of only limited value, so what I thought was I had a look around to find another way of doing it that did not use these obsolete chips. And what I came up with, and I've never used these, so it's going to be interesting. These are GALs. This is a GAL 16V8. So here comes this board, ATF 16V8. These are 20-pin chips, and they're a little bit bigger than the 18-pin chips for these, but not very much. So with a little bit of relaying out the board, I managed to fit that all on to basically the same size PCB. This is a bit bigger than this one, I do believe that these gals are available as surface mount devices which are smaller, so we could probably shrink that, but I don't really want to do that at the moment. So how do we get to our PCBs? Well, we start off with KiCad or KiCad, however you want to say it, and this is the schematic for the MC14495 version. So it's actually a version 1.2 because I've fixed a couple of things that were bugging me about the one that we're going to build. They are that these capacitors are the wrong size on the PCB. I made the holes too small, and also the connections on this main pin header are backwards, so the way I've got it on the board, the digit on the left is the pins on the right and the digit on the right is the pins on the left, which is kind of backwards. So I've sorted that out, and then we lay that out as a board, and this is my layout. You'll see it's actually slightly different to the one that we're building. I've made it a little bit neater. You can have a look at that in 3D view. There you go, that's the front and that's the back. Now if you happen to know what this quote comes from, then please tell me in the comments. It's no prizes or anything, it's just a little bit of fun. So in order to upload this to PCBWay, we need to produce a set of Gerber files. And to do that, we simply go to plot on here and we say generate drill files. Yes, it's in a folder called Gerber. You need to do that. That is all the holes. Then we do the main plot. That's done. Excellent. Now, in order to send it to PCBWay, we need to zip these up. So we're going to call this, there we go, Blinking Hex 2 version 1.2. So now we can go to PCBWay and we'll go for a quote. We still have our purple solder mask offer, so we're going to go for that. Upload our Gerber files, add Gerber, and here we are. So that's the Gerber file that we created. Up it comes. It tells us the size, 50 by 39, and we can pick our options, which is going to be purple PCB. There you see we have our special offer, $5 with white writing, and we're gonna have 10 because you get 10 for your $5. Agree. So $4.85. If we leave this for a bit, it will come back and it will show us, it will work out the Gerber file and show it to us. So we'll do that. It's been a couple of minutes and now you can see we've got representation of our PCB in this window here, and we can just have a look at it and the Gerber file view. So that just gives us a verification that we are making the board that we think we're making, and then proceed to checkout. Now I personally go for global standard. It's a few days longer, but it's a lot cheaper. We won't see the results of this in this video, but next time we will open the box and see what we got. What we'll do is we'll build a couple of these up and then we will plug them into a Commodore 64 into the user port, and we will write a little program in BASIC and see if we can get some numbers out. So these are fairly simple little circuits. We just need some IC sockets and some capacitors, and on the back of this one some resistors. So we'll build these up first. I'm just going to build two of them so we've got a spare. So I'm a bit short of sockets. We have to use turn pinned ones on these, unfortunately, because I don't particularly like turned pin sockets. First thing we need to do, of course, is clean the board. So we're going to use some IPA The top is less important because that's not where we're going to be soldering. The back, of course, is the important side. So let's put those two aside to start with, and we'll build these two. I'm going to do a quick test to see which is lower or which is higher. And that's interesting. The capacitors I've got don't match the hole size that I'm making. I made these holes too small for these capacitors, so I'm going to have to bend these in order to get them to fit. So what I'll do for the next revision of this board is basically relay it out with a bigger footprint. So that's going to be a bit rough and ready, but never mind. We can just measure this gap using the back of this. Now, we built this in a previous video. I'll put a link up in the corner. You can check that out if you haven't seen it, and I can almost guarantee you haven't seen it because I've seen the analytics. So on the back there is a handy little measuring guide, and we can just say, where is it? There we go. So we can just measure that up and say, oh, that's about 3 millimeters. And these I know are going to be, I should measure this before I bent it, but yeah, 5 millimeters. So handy that. It's got all the SMD sizes on it as well. Now we're not going to spend too long on the actual build because it's a fairly straightforward build. So we're going to concentrate mostly on making it work. So I'm going to put 2 sockets in here. We'll just build one. Turn it over. You've seen the technique. Blob in the corner and another blob in the opposite corner. And then very quickly just run down it and solder the pins. Now this little solder blob here is to do with how it's going to clock the data in here. It's latching, and we can either have it basically latch on a clock signal, which is going to be that pin here, or we can set it to ground, in which case it's just going to be free running and show whatever's on there. For the connector, I'm just going to use regular 0.1 inch pitch pin header, and I've pulled one pin out. So it's basically a 12 pin strip of 0.1 inch pin header with one pin pulled out, and I'm going to mount that on the back. You can of course use right angle pin headers or any other shape and have it, so that it's mounted vertically. I'm going to mount it horizontally, and then basically we'll solder one pin and then get it straight. So the final thing is these 2 7-segment displays. Like any other chip, they go the right way around. So all we've got to do is put these chips in and we are done. There we go, that's the first one. So this is using the regular MC14495E, and there's one obviously for each digit. So this is for D0 through D3, and this is for D4 through D7. This is the second board because the first time I think one of the cameras was not turned on. So we're going to start with the SMD stuff, and that is on the back. I've already got the resistors lined up ready to go on. I've sorted them into the right way up order because I'm just a little bit about that. So the way we do this is exactly like we did it with the practice board last time. You put a little tiny blob of solder down one side. There's 14 resistors, 7 on each side, because of course it's a 7-segment display, And although each display has 8 LEDs, because of course the decimal point, we're not using the decimal point, and so we just need 7. Plenty of flux, that's going to do both sides. So what we do is we melt the solder, place the resistor down, slide it on. Melt the solder, line up the resistor, slide it on. I'm doing this by eye without the benefit of the microscope, so it's likely to be a little bit jaggy. We will of course need to clean all this flux off, but we can worry about that at the end. We'll just live with being a little bit messy for now. Then we've got plenty of flux, we don't need any more, so we can just go down. Okay. So now it's pretty much the same as for the previous board. We're going to put the chip sockets on, making sure to get them the right way around, of course. Now these resistors are actually 510 ohms because I didn't have enough 470s to do 2 boards. So that means that the display on this is going to be a little bit less bright. But will it make a difference? I think probably not. These 7-segment displays are green compared to the red ones of the other chip. And finally we put the pin header on. Now I'm going to use the other board just to support it, so that it's going to be roughly the right orientation. Finally, let's just give it a bit of a clean. And there it is. Now we don't put the GAL in because of course we need to program it. And I haven't done that before, so that is going to be an interesting thing. In order to figure out how to program these GALs, we need to work out the truth table of the 7-segment display. This is a 7-segment display. It has 7 segments and of course a decimal point that we're not really interested in, and they are labelled A, B, C, D, E, F and G. So for every input on our circuit from 0 through F, we've got an equivalent binary value, and we know that input 0 lights up A, B, C, D, E, F, but not G. So this is our truth table, and we can work that out for each one of these digits and get exactly which LEDs should be lit for every character. And that is our truth table, and that is what we have to program into the GAL, because each of these is going to be a pin on the output, and that is going to drive our 7-segment display. So to do that we use a tool called WinCouple. So this is going to take an input file and compile it into a JED file, which we can then use in our programmer and program the device. So I've got an input file here, and I don't claim originality for this because I really don't know what I'm doing as far as GALs are concerned. So this originally came from a chap called Mbakula on 6502.org, and I'll show you that. So you can see the URL here, and if you want to go check it out yourself, you can do so. This is his original code, which I have borrowed, and this is organized for common anode, while my device is a common cathode. So you can see here I've had to basically invert everything, because with a common anode, a 1 is going to be a 0 on a common cathode. So that's the code adapted for being common cathode, and that matches our truth table. We then compile that. And it's compiled, and that will have produced a JED file. Here we are, 7segment.jed. We can look at that in a text editor, and you see it's basically just a sort of lookup table. Now we come to load XG Pro and actually program our devices. So here's our T48 programmer. So we can get our GAL, that goes in here. Now this is already set up for a GAL 16V8D. This is a D device. So just like any other chip, we can open the file 7segment.jed. That has produced stuff. I'm not going to pretend to know what that is, but that is stuff. So there are some things to check here. So we do pin detect, erase before, verify after. We don't want to encrypt the chip, because that is a possibility, but if you encrypt it, you can't verify it. So we'll turn that off and then program. Flash, lock bit, beep sound on, GAL 16VD, go. Done. Now, because there are two devices, we need to program two chips. So we just drop the next one in, hit program again. Done. So now we can stick those into our blinking hex and see if it works. So this is the end result. We have our MC14495 and we have our GAL 16V8. They both basically do the same job, and they will display for an 8-bit input the hex value of that 8-bit number. Well, how are we going to test this? Well, I have knocked up this little test board, and this is basically the prototype board for the Commodore 64 user port that we used in a previous video when we were playing around with sensors and temperature measurement and so on. I've just taken all the bits off and we are reusing it, because why keep making new boards when you can reuse the old ones? So it's going to go on here like that. In the Commodore 64 Programmer's Reference Guide, we have got the information about the user port, and this tells us the pinout for the port. Here we have all the details. On the bottom side, pins C through L are port B on CIA chip 1. So that is entirely programmable by us from BASIC. And this is the wiring for that. So one thing that I immediately noticed when I set about just making this wiring diagram is that on here I've got the pin connections arranged D0, D1, 2, 3, 4, 5, 6, 7. that seemed to me to be logical at the time, but when you think about it, it's not so much, because this is going from the least significant bit to the most significant bit, and that is the most significant nibble, 4 bits, and that is the least significant nibble, 4 bits. So these pins are going to that chip, and these pins are going to that chip. And as you can see on the wiring diagram, that is all crossed over, since D0 is at that end and D7 is at that end. If I come to do a revision 2, then I'm going to swap that around so that it actually is a little more sensible. But, you know, it's a first prototype, we live and learn, don't we? So pin on that end is 5 volts, that goes to pin 1, which you can see is the red wire. And ground on the other side, I've got a strip down there, that goes to either pin 12 or pin N, and they are both ground. The clock wire goes to pin M, which if you look in the manual, pin M is PA2, which is the A2 line of, or which is port A of CIA1. So we're looking at port B as the main thing, but that is port A2. And in fact, we actually end up not using that, so yeah, we don't need it. I thought we might, it turns out we don't. So let's plug it in, write a program, and see if we can make the LEDs go. Here we are, we're using the green Meanie. Let's plug this one in first. We're going to try them both. So this is the MC14495, which has series resistors built into the chip, so there's no resistors on the back. It's just exactly as it comes. So let's power it up. FF, that's a good sign. Now we can write a little basic program. I'm referring to the programmer's reference guide here for the numbers. So the first thing we want to do is set the data direction register, which is 56579, and we set that to 255, which is all outputs. Then we're going to write a little program to count through all the numbers so that we can see all the digits on the display, and it goes from 0 to FF. We can see it's FF at the start because basically all the output lines are high by default. So for I equals 0 to 255, poke 56577, comma I. Next. That should go through all the numbers, and that is going to repeat and loop around. Let's see what happens. And that's going around, but it's kind of fast. So let's edit this. I'm going to take that next out. In line 30, I'm going to add in a delay loop. What shall we have? 100 or, yeah, let's make it 100. Close both loops. And that is much slower. We can read that now. We can see all the numbers. Still a little bit fast. We could slow down the loop and have that count even slower. We could do it, you know, 1 per second. Or whatever, but that is definitely going. So stop that. Now let's see whether the other one works. So we're going to turn it off and swap it over. Okay, switch it on again. See if it goes. FF. Now these ones are green, so we're going to need to type in the program again because I didn't save it, because I don't have any savey stuff plugged in. So, one moment please. Okay, there we are. The program is typed in. So let us run it. And that's the GAL version. So what you're saying, it's very nice having a thing that displays a number in hex, and but what use is it? Well, we can do exactly like we're doing here and display the values from a port. We could use that on a data bus. We could display data addresses. We could display any 8-bit value that we particularly want to have a look at, and have a look at it in hex rather than just as an array of lights. We don't have to plug that into a C64. We could plug it into a breadboard. We could use it with an Arduino, with a Raspberry Pi, or whatever. It's a nice little general purpose self-contained circuit. And I'm using it with a Commodore 64 because of course we all like doing stuff with a Commodore 64. And I think it's been said before, I'll do anything with my computers that is not playing a game. But where next? We've got an 8-bit value, so the logical next step is going to be adding them together and giving us a 16-bit value. But the way that I've done this is not particularly scalable, because that's driving all the LEDs at once, at the same time. We've got 2 chips driving 2 LEDs. 1 chip drives each LED, and it's the same with this one. There are 8 inputs to these GALs, but we're only using 4 of them. So in theory we could put all 8 inputs into one GAL, but we can still only drive 1 LED because we've only got 8 outputs. So what we can do is we can multiplex them, and we can essentially switch between that one and that one, displayed by this very fast, at least fast enough not to be able to see the difference. And this is how a lot of numeric displays work. If you look at them on camera, you can quite often see them strobing. That of course is not visible to the naked eye. So we can do that, and I've been thinking about the version 2 of this circuit while we have been building this one. I hope you've enjoyed this what I think is an interesting little diversion into messing around with some blinking lights. And if you have, please click on the like button and subscribe if you're not already. Check out my Patreon, all the usual stuff. You get early access to videos, you'll get your name in lights, not necessarily blinking lights, but certainly in the credits, and every little bit helps the channel. I'll see you next time. See ya. Bye.